We continue our discussion of more advanced concepts of ionic equilibrium. We'll continue with acid-base titration curves, looking now at weak acids and weak bases. Then we'll go through solubility of nominally insoluble compounds, and then we'll take one brief look at complex ion formation. In our last video, we looked at a strong acid, strong base titration curve. We now know how that works. Next, let's consider the reaction of a weak acid with a strong base. How does this work? Well, as we add strong base to the weak acid will form its conjugate weak base. And so in the early stages of the titration, we create a buffer because we have our initial weak acid with some weak base that's formed. Eventually, we'll reach the equivalence point. At the equivalence point, we will have converted all of our weak acid into a weak base, and so we expect the pH to now be greater than 7, unlike the strong acid, strong base titration. And when we go past the equivalence point, then the strong base takes over control of the pH of our system. We've exceeded any buffering ability, and it is now a strong base solution. Let's see how we handle the calculations for the titration of a weak acid with a strong base. Our initial pH is controlled by the pH of the weak acid. We know how to handle that from our work in chapter 18. Our acid dissociation constant is given here, and we can calculate the hydronium concentration from the square root of the product of the Ka times the initial weak acid concentration. And from that, we can get our pH. As we move from our initial point to our equivalence point, between here, we have our initial moles of weak acid, calculated from the molarity times the volume. We've added strong base, but the strong base is smaller in amount than is the weak acid number of moles. So the moles of weak acid that will remain will be the moles of weak acid we started with, subtract off the moles of hydroxide we've added, and the hydroxide that we've added will produce the weak base. So the moles of weak base equals the moles of strong base that we added. We can go back to our weak acid equilibrium constant expression, or the Henderson-Hasselbalch equation, and we can plug in our value for our pH, equaling the pKa plus the log of the amount of base divided by the amount of acid. Once we reach the equivalence point, now we will have added as much strong base as we had weak acid initially. Therefore, all of the strong base has converted the amount of weak acid we had over into weak base. So we use our weak base equation. Kb is Ha times OH minus divided by A minus, or the hydroxide concentration is the square root of Kb times the concentration of weak base. So we can calculate our pH using our standard equations with which we've worked in the past. Finally, as we go past the equivalence point, we've consumed all of our weak acid. Now the strong base controls. So the moles of strong base in excess equals the moles of base we've added minus the initial amount of weak acid that we had. The strong base then is equal to, strong base concentration is equal to the moles of excess strong base divided by the volume of acid plus volume of base. We can calculate pOH, and from that we can get pH. Let's look at the reverse. Now let's take a weak base and titrate with a strong acid. Initially, our pH is above 7 because we have a weak base. As we add strong acid, that converts our weak base into weak acid, creating a buffer. We have a weak acid-weak base pair. Once we reach equivalence, all of the weak base has been converted into weak acid, so our pH is below 7. As we go past the equivalence point, the strong acid takes over. Here are our calculations. Using all of our standard equations, our initial pH will be controlled by our weak base equation. Our pOH is given, and then we can calculate pH from that value. Our hydroxide concentration will be the square root of Kb times the initial concentration of weak base. The pH before the equivalence point, after we've moved past our initial pH, once we've added some acid, we'll have a buffer. So we have some initial moles of base. We've added strong acid to this. The moles of weak base that remain will be given by our moles of initial base. Subtract off the moles of strong acid added. And then the moles of weak base will be equal to the moles of strong acid we've added. We can use the Henderson-Hasselbalch equation again. The pH is equal to pKa plus the log of the remaining weak base divided by the weak acid that we have produced. When we get to the equivalence point, we will have converted all of our weak base into weak acid. So we use our corresponding weak acid equations. So we have the initial moles of weak base divided by the volume of acid plus the volume of base. That gives us the concentration of weak acid. We can use our equation from earlier where the hydrogen ion concentration is the square root of Ka times the concentration of weak acid. And from this, we can calculate our pH. Finally, as we go past the equivalence point, strong acid takes over. We calculate our moles of strong acid, subtracting off the moles of weak base we initially had. That gives us our excess moles of strong acid, divided by the volume of acid plus volume of base, gives us our hydronium concentration, from which we can calculate the pH. Now, we generally don't work with weak acid, weak base titrations. We're not going to discuss them in this course, but you will see them in more advanced courses. So the next thing we're going to look at are acid-base indicators. An acid-base indicator is organic acid that is a weak acid, and it has a different color in its acid and base form. So we can see the equation here. We start off with a weak acid, HIN, IN meaning indicator. And that's our weak acid form having color A. And then when we put this in solution, that weak acid can convert into weak base, and then the weak base will have a different color. So when you pull the proton off, that changes the molecular structure, and that molecular structure is correlated with the absorption maximum. Now, the ratio of weak acid to weak base is going to be controlled by pH, just as we've seen for all of our weak acid, weak base systems. So the indicator can be used to monitor the pH change during an acid-base reaction. Typically, the color of an indicator will change over a specific and relatively narrow pH range of approximately plus or minus 1 pH unit. That would be a total of 2 pH units. So on the acid end, you have your pKa minus 1. If your pH is at that level, you'll have your acid color. As you move through the intermediate range, you'll have a mix of weak acid and weak base. And as you go to the base end, you'll have a second color. Here is a graphic that shows a number of common acid-base indicators shown in the upper graph. You can see, for example, crystal violet. That changes pH at a very low value of around 1. Thymol blue, which is diprotic, actually has 2 color changes associated with it. A number of others showing their pH changes at different values. So you can see that if you had equivalence points at different locations, you could select an indicator which would change color near your equivalence point. On the bottom panel is shown bromethymol blue, and bromethymol blue has a color change around the upper 6 region, and you can see that it changes from yellow in the acidic conditions over towards more of a blue-green at the alkaline conditions or higher pH conditions. So here we see 3 different acid-base titrations. We've first got a strong acid, strong base titration in the upper left. And of course, for a strong acid, strong base titration, the equivalence point pH is 7. And you can see that there's a very large pH change right around the equivalence point. So from, volume of about 39.5 to 40.5, you can see the pH changes almost 10 pH units. In this case, there's a wide range of indicators that will work. So for example, phenolphthalein would work nicely. So phenolphthalein is shown with its non-color to pink color change here, even though it occurs around high end of the pH 8 range. You'd still have a dramatic color change when you are near the equivalence point. Even methyl red, which has a pH change much lower, still works. Now, if we go to a weak acid, strong base titration on the upper right-hand side, you can see that right near our equivalence point, it's much more important to have a indicator that changes, because our pH change for a weak acid strong base titration curve is much smaller than a strong acid strong base. You can see that near the equivalence point, the pH may change a total of approximately 4 to 5 units, but that's a much smaller range than the strong acid strong base titration. So in this case, phenolphthalein will work. You can see that right near the equivalence point, the color will go from clear to a red color for our phenolphthalein, but methyl red would not work. You can see methyl red starts out as red and turns to orange well before the equivalence point, and you would not get a good reading on the equivalence point or end point of this titration. Finally, if we have a weak base with a strong acid, you can see in this case, phenolphthalein would do very poorly, whereas methyl red will do a much better job in this case, giving its color change right near the equivalence point, so our reading of the endpoint when the methyl red changes color will work out nicely. Finally, let's mention polyprotic systems. We know that there are a number of polyprotic acids that are very important, phosphoric acid being one that we commonly experience, consume, and use, sulfurous acid, and many others that we've seen. Here we're going to look at the titration of a weak polyprotic acid, that is sulfurous acid, with a strong base, sodium hydroxide, just using this as an example to show how the titration proceeds. Initially, we have weak acid. The sulfurous acid has a pH well below 7 because of the acidic conditions in our diprotic system. As we add strong base, some of that weak acid gets converted to amphilite. That is, the sulfurous acid gets converted to the monohydrogen sulfite anion. That's a conjugate acid-base pair, and it is a buffer. And the buffer is a low pH buffer, but it is still a buffering region. So we see buffer here, and then we reach what we call the first equivalence point. That is when we've added a number of moles of sodium hydroxide that is equal to the number of moles of sulfurous acid. We can completely remove the first proton. Once we reach that equivalence point, then we have pure or nearly pure monohydrogen sulfite. We're not going to go through the pH calculation here, but it's a relatively straightforward calculation. And then, as you go past that first equivalence point, you reach a second buffer region. That's where we have the monohydrogen sulfite and the sulfite conjugate acid-base pair. This buffer has a much higher pH, so this buffer's in the higher pH region near pKa2 for sulfurous acid. Now there's a second equivalence point in this reaction, because this titration we can add 2 moles of hydroxide to consume both of the hydrogens in sulfurous acid. So the second equivalence point now we have the weak base sulfite. And then once we go past that, then we'll have a strong base solution. Amino acids are polyprotic acids. They're very important ones. Amino acids have the general structure NH2 with a central carbon, which can have 2 functional groups on it, and that's attached to a carboxylic acid moiety. And for naturally occurring systems, then R is a functional group that can be one of 20 different chemical structures. So amino acids contain a weak base part, that is the NH2, like ammonia, and they contain a weak acid part, like acetic acid, a carboxylic acid. So both the amine and the carboxylic acid groups are protonated at low pH. As the pH of the solution goes higher, the proton does not come off of the weak base amine part first, it comes off of the carboxylic acid. It creates what we call a Zwitter ion. That is, an ion in solution that has a plus and a minus together on the same molecule. Seems unusual, but that's the most stable structure for an amino acid at nearly neutral pHs. Then as we go to high pH, we can pull off the amine proton to create the fully unprotonated amino acid, which will have a negative charge on it. Now we're going to move on from acids and bases, and we're going to look at slightly soluble ionic compounds. I want you to think back much earlier to Chapter 4 in General Chemistry 1. We learned about soluble and insoluble compounds. So soluble compounds are ones that would go into solution, form an electrolyte, they would carry current, they would have free charges available like sodium chloride. And then there were insoluble compounds that we said didn't dissolve. And an example would be for, lead sulfide as an example, or cadmium sulfide. Sulfides tend to be insoluble, and for those with transition or heavy metals or main group metals, they tend to not dissolve in solution. But that's only an approximation. An insoluble ionic compound is actually slightly soluble in aqueous solution. A very small amount of such a compound will dissolve, and it will dissolve and dissociate completely. So we have an example here. Lead fluoride would be one of the example compounds you had from Chapter 4 that was insoluble, but it turns out to be slightly soluble in water. And there's an equilibrium that exists between the solid compound, that is lead-2 fluoride, PbF2, and its corresponding ions, the lead-2 ion and the 2 fluoride anions. We can write out a concentration ratio, and we can see here that the lead concentration times the fluoride concentration squared, but it's divided by the lead-2 fluoride concentration will equal Q. And of course, remembering back on our equilibrium constants, lead-2 fluoride is a solid, and as a pure solid, we put down its concentration as 1. So we have what we call the ion product constant, that QSP will be the product of the ion concentrations in solution. So QSP, the ion product concentration expression for slightly soluble ionic compounds, is shown here. For the slightly soluble compound M sub P X sub Q, which consists of M plus ions and Q Z minus ions, we can write out the following ion product expression. If a solution is saturated, that is, we've thrown in enough solid so that there's some solid sitting at the bottom of our solution, we will have something that is called saturated. That is, the ion concentrations will have reached their maximum equilibrium values. So then the QSP is equal to what we call the KSP, which is called the solubility product constant. That's a special name for that equilibrium constant. The KSP for a salt, then, is a measure of how far the dissolution proceeds at equilibrium, that is, the saturation concentrations. And we can predict whether a formation of precipitate will occur or not. So if we have a saturated solution of a slightly soluble ionic salt, QSP will equal KSP. And KSP, that's the thing we find in tables. When two solutions containing the ions of a soluble salt are mixed, if QSP is equal to KSP, the solution is saturated, it's at equilibrium, and no change occurs. So we can look up the KSP in a tabulated value in tables of KSP values, and if our QSP is equal, then we'll have a saturated solution. If QSP is greater than KSP, that means we have a supersaturated solution, and typically the precipitate will form until the remaining solution falls back down to the saturation value. That's called crashing out of solution or precipitation. If, however, QSP is less than KSP, there'll be no precipitate present because the solution is unsaturated. The ion concentrations are below the saturation limit. Here are a series of solubility product constants for some common important ionic compounds. There are many thousands of these that are known. So you can see aluminum hydroxide, cobalt 2 carbonate, iron 3 hydroxide, and so forth. The corresponding KSP values tend to be very small numbers. Typically, these insoluble materials will have KSPs that are below on the order of 10 to the minus 4 to 10 to the minus 5. There's a relationship, of course, between the KSP and what is sometimes termed the solubility of a salt at 25 degrees Celsius. A larger KSP means there's a larger solubility or a greater solubility. That is, when comparing compounds that have the same total number of ions in their formulas. So here we see for the first three, magnesium carbonate, lead 2 sulfate, and barium chromate. These are each 1-to-1 divalent salts. And you can see as the KSP decreases going from top to the third one down, the solubility decreases. The same thing happens when we have 3 ions produced with similar charges. As the KSP decreases, the solubility decreases. The common ion effect is observed as well. So here we see lead 2 chromate. It's looks like Big Bird yellow solution. On the left-hand side, it's a slightly soluble salt. When the lead 2 chromate is thrown into water, you get a slight dissolution of lead and chromate. On the right-hand side, if we add a little bit of excess sodium chromate, we do a Le Chatelier's effect. We've now put in some product that will drive the reaction towards the reactants. That means we get more precipitation, and you can see extra yellow materials formed at the top of the test tube. An important factor is when we combine together solubility with acid-base chemistry. This is extremely important for environmental and geological processes. Changes in pH can affect the solubility for many slightly soluble ionic compounds. This is particularly important when adding acid increases the solubility of a salt that contains a weakly basic anion. An example would be calcium carbonate. Calcium carbonate is the primary component of limestone, as we'll see in a moment, and this dissolves in water to form calcium and carbonate. Carbonate is a base, being able to react with acid to form bicarbonate, the bicarbonate which can react with acid to form carbonic acid, which can produce carbon dioxide gas. So, adding acid to calcium carbonate removes carbonate ions. A Le Chatelier's effect, where we remove some of our product, that forces the reaction towards the right, causing a shift in the equilibrium towards our products. More calcium carbonate will dissolve and our calcium concentration will increase. Here we can see a picture when a carbonate mineral is treated with hydrochloric acid, carbon dioxide is produced. This is very important in thinking about cave formation. Limestone is mostly composed of calcium carbonate. Dolomitic limestone will have some magnesium, and there can be small amounts of other metals present. Calcium carbonate is a sparingly soluble solid with a KSP of 3.3 times 10 to the minus 9. When groundwater, that is water under the ground, which is rich in carbon dioxide, which you know is an acid, trickles over calcium carbonate, it causes it to dissolve. And when this occurs over centuries and millennia, this can gradually carve out a cave. Now, when water that contains bicarbonate and calcium drips from the top of a cave, the air into which the water is dripping has a lower partial pressure or concentration of carbon dioxide than the soil does. So that causes some of the carbon dioxide to come out of solution into the air, and that shifts the equilibrium. As the carbon dioxide comes out, the solution becomes more alkaline because the acid is leaving, and then we get calcium carbonate reprecipitating. So remember before on the previous slide, when we added acid, we form more product. If we remove the acid, we'll form more reactant, that is the calcium carbonate. And this is how stalagmites and stalactites are formed within caves. That is those long protrusions of solid material. The reaction is shown here. Carbon dioxide can dissolve in water, and that can form an acidic solution. Calcium carbonate can react with the acid to form calcium and bicarbonate, but then when the carbon dioxide is removed and goes back into the atmosphere, we can send our bottom reaction back towards the reactants to reform more calcium carbonate. So the formation of caves and the corresponding structures inside those caves are driven by acid-base chemistry and precipitation chemistry. And this is very well understood geochemistry now. Another place where this is very important is in acid precipitation, or what's termed acid rain. Since pH affects the solubility of many slightly soluble ionic compounds, the formation of acid rain can have far-reaching effects on many aspects of our environment, and that's shown in the graphic here, where sulfur dioxide and nitrogen oxide emissions from transportation vehicles or coal-fired power plants can release acid into the air. This acid can result in lower pH precipitation. In higher lakes that are higher altitude that are bounded by limestone, they can be buffered. pH changes can be relatively small, but in certain regions where there is soil that's low in limestone, like the Appalachian regions, they can become very acidic and can kill off aquatic wildlife. Our last topic in Equilibria is going to be the formation of complex ions. We're going to go through this briefly. A complex ion consists of a central metal ion, and typically that metal ion is thought of as a Lewis acid. It's an electron pair acceptor, and it is covalently bonded to two or more anions or molecules that have lone pairs that are electron pair donors. These are Lewis bases, and these electron pair donors are called ligands. So we'll have a metal bonded to a ligand. So here we see, for example, the chromium-3 ion with 6 ammonias attached to it to form an octahedral complex. We see 6 groups that are all symmetric around the metal ion. This is a metal complex, or a complex ion. Complex ions can be formed in water. So when a salt dissolves in water, the complex ion forms. The water initially acts as a ligand and bonding to the metal. So often when we have a hydrated metal in solution with another ligand, the bound water is replaced by another ligand. So for example, if you have a metal with 4 waters and it forms the corresponding ammoniated ion in aqueous ammonia, we can write out the reaction as follows. We typically don't write the waters in directly. We'll just write the metal 2 ion, the 4 ammonias to form the metal ammonia tetra ammonia complex. And so the formation constant, that is the equilibrium constant for this process, is shown down below. And in fact, this typically does not occur in one step. It'll occur in 4 sequential steps. You'll add 1 ammonia, a second, a third, and a fourth. And there'll be a formation constant for each one of those steps. But we're not going to go into detail in this class on that. You can get that in a more advanced chemistry class where we'll look at it in detail. It's a very important process. So here are some common KF values. You can see that these can be very large values, some as high as 10 over 10 to the 40th power. So these can be very stable complexes that are formed. Finally, we can look at aluminum hydroxide, which turns out to be a very important material. Aluminum is the most abundant metal on Earth, and it's used in very large quantities. It consumes approximately 5% of all the electricity on Earth just to produce metallic aluminum, which is used all over the place and all throughout our technological culture. And you can see that here we have aluminum hydroxide in the center, and we can write aluminum hydroxide as AlOH3, but it turns out when we throw this in water, there are 3 water molecules that attach to it. And if we add strong base to this will form the tetrahydroxoaluminate ion that is moving towards the right. If we add acid, we can dissolve the aluminum up and we can form the hexaaquo, which is the term for 6 waters, aluminum complex. This is very important with something called the Hall-Héroult process, which you can look up, but we won't have time to cover in this class. That completes our study of Chapter 19.